Hello, I welcome you all in this presentation on the laser welding related with the subject joining technologies for the metals. This is one of the radiation based processes, another is the electron beam welding, and both these processes are known to offer the higher power density, wherein right from the heating to the melting and evaporation can be achieved by adjusting the power density suitably. So, in this presentation mainly I will be talking about the laser welding. Laser welding is basically the abbreviation of light amplification by stimulated emission of radiations. So, in this process basically one source of energy. So, using laser basically one form of energy is converted into the radiation energy or the electromagnetic radiations. So, energy may be in form of electrical or thermal, that is converted into the electromagnetic radiations. These radiations include all types of ultraviolet radiations, infrared radiations, and also the visible light radiations. So, from these radiations basically the single wave length radiations are obtained, which are called monochromatic radiations, which are used for processing of the material. So, how it is done and how it is achieved, that is what we will try to see. In this one basically the most common way is to that the lamps, mainly called flash lamps, are used to excite the material, mostly in form of say ruby crystal, and from this after the excitation the laser radiations are emitted like this, then they are reflected back using suitable reflectors here like this, and then they are brought to the parallel, then through the lens it is focused at the desired point, and this point becomes the workpiece. So, when they are targeted or applied or directed over the surface of the workpiece, so using flash lamps light energy is directed, which excites the material, which may be in form of the gases or the ruby crystal gases like helium or argon or carbon dioxide can be used. These are the reflectors which will be reflecting and focusing all these things towards the lenses, and these lenses will finally be converging it onto the surface of the workpiece, and whenever it is directed over the surface of the workpiece, the kind of energy density or the power density that we get becomes extremely high, which may range from like say 10 to the power 3 to say 10 to the power 8 per mm square or more. So, in that case there is a lot of flexibility to achieve very wide range of the power density, and this feature is exploited for the various purposes in processing of the material, which includes so by regulating the energy density we are in position to use it for the heating purpose, which is basically used for the like say laser hardening, material is heated rapidly to the at the surface, and then by auto quenching or by external quenching it can be hardened. So, like say the surface is directed with the laser, and here it gets heated, reaches to the austenitizing temperature, and then it is quenched off as laser moves away from the directed surface, and then this quenching results in the hardening of the surface layer. But for this it is necessary that material has a hardening characteristics, which is primarily say for medium or high carbon steels and cast irons. This method is found to be suitable. Similarly, this is also used for the melting purpose. Now, melting when the laser is used for the melting purpose, we need much higher density as compared to that for the heating, and this can be used for the welding, where fusion of the faying surface is achieved, may be used for the brazing purpose, may be used for the alloying of the surface layer, alloying of the surface layers like this, and it is also used for the controlled removal of the material, which we can say that machining. So, this is what we normally call as a machining, and in this one basically the evaporation or ablation of the material over the directed surface is achieved. So, that the controlled removal of the material takes place in order to obtain the desired geometry and the sizes of the surface of the material. So, the machining, welding or the melting and heating all can be achieved by adjusting the power density of the laser being applied over the surface. So, there is one very general guideline kind of the diagram which will help us to see the kind of approach which is used. Here in the x axis we have the exposure time. Exposure time means the time for which the laser is applied. So, here extremely small, say minus 10 10 to the minus 10 10 to the power minus 4 and 10 to the power 0. And in the y axis we have power density or energy density, which is in watt per mm square. So, here say 10 to the power 4, 10 to the power 8. So, if we see this is the band for the band which is used for the purpose of the heating goes in like this, and the band for the purpose of the metal. So, there are 3 zones basically. Combination of the power density as well as exposure time can be used for the different purposes. This is the zone for the heating purpose, means it is used for the heat treatment purpose or softening of the material like bending. So, this location lies for the say bending purpose, where very short period the laser is directed. So, material gets softened and then it is after softening it is bent by applying suitable pressure. Similarly, these are the bends for the heat treatment purposes as far as the power density and the exposure combination is concerned. And then we have the like say welding. So, welding lies somewhere here like slightly more than 10 to the power minus 4 seconds, and here 10 to the power 4 or more power density, and further higher power density and shorter exposure periods are used for the purpose of the alloying of the surface, wherein the material to be alloyed is laid over the surface and then laser beam is passed over the surface, so that the controlled fusion of the base material and the material overlaid on the surface fuse together and results in the alloying. of the surface, and the brazing is used here for the lower power density for the longer periods, like say this is the kind of a zone for the brazing purpose. And then this is the area where, so this band between the two corresponds to the melting and then evaporation or ablation. So here the higher power density for longer period, lower power density for longer period, and higher power density for shorter period. So more than 10 to the power 8 power density is normally used for the means for the evaporation and machining purposes. So that is somewhere here for the machining, the power density and the exposure time combination for the machining purposes. So basically if higher is the power density, we need a shorter exposure time for generating the heat. Depending upon the purpose of the using laser, we may use it for a very short period, like so just for softening purpose, higher power density for soft purpose for short period, and somewhat very high power density for somewhat longer period for the machining or the cutting purposes, and for the laser for the brazing purpose lower power density and the longer period. Similarly somewhat moderate power density and the longer exposure period is used for the welding purpose. So this is how this is a general broad this diagram gives the broad idea about the kind of the exposure period and the power density is to be used for the different purposes. Now how to get the suitable exposure time for this purpose? Normally say this is the surface of the workpiece. So now we can direct the laser at a particular point. Normally the using the CNC table over which workpiece is mounted is moved with respect to the laser. Laser is normally directed at one location and position of the workpiece is adjusted using the controlled movement using the numerically controlled machine tool. So now the speed of the movement can be adjusted suitably in order to have the required exposure time. It may be very slow for longer exposure period and it may be very fast for the shorter exposure period. So the speed of the movement means the relative speed of workpiece with respect to laser beam determines the exposure period. So normally what we do, higher scanning speed, laser scanning speed or the workpiece speed with respect to the laser is used for the shorter exposure periods. So depending upon the combination of the power density and the scanning speed, suitable joints are made. For example, like say the laser we may use of the CO2 laser or ND-YAG laser. This offers the short wavelength laser, and this is of the CO2 laser is the of high wavelength laser which is about 10 to the power 6 micrometer, and here it is 1.0 something micrometer. So the short wavelength lasers, they reflect less as compared to the high wavelength lasers. So here if this is the surface of the workpiece and we are directing the laser over the surface. So the diameter over which a laser can be focused is very small. Say in case of ND-YAG laser, typically say 200 to 400 micrometer. So the beam is focused over the surface. It may be of say it is common to have the 1 to 2 kilowatt lasers, while CO2 laser can be as high as 25 kilowatt capacity. So the wattage of the laser matters a lot in delivering the power over the surface. So higher is the power which is available with the laser, it can deliver lot of energy over the smaller area. in short period. So, say for 1 a kilowatt laser or 500 watt laser, it is if it is focused over the surface of the area over which it can be focused, say 200 micrometer for say typical value for the NdYAG laser, where here Nd is neodymium, yttrium, garnet, aluminum, garnet. So, these are the three abbreviation for the neodymium, yttrium, aluminum, garnet laser. This is one typical laser, and in this case what we do, laser is directed over the very small area. So, the melting takes place. So, you see melting will be taking place like this. So, if you keep on increasing the duration of the stage, the depth of penetration will keep on increasing up to a certain limit. So, we have to identify that how to adjust the scanning speed, so that we get the suitable depth which will be sufficient for penetrating through the thickness, and once this depth is achieved, we can start moving the laser as per the required speed. So, the speed of the relative movement, like the relative movement between the laser and the workpiece is determined using suitable. So, you can say the laser or workpiece speed, whatever is used. So, it will help us in determining how much energy is being delivered in unit length, and then the power of the laser certainly matters, power of laser. So, increase in power and increase in speed, increase in power and decrease in speed will increase the power being delivered or energy being delivered to the workpiece, and so it will increase the depth of the penetration and the size of the weld which will be made. Now, as I have said, since the laser is directed over a very small area and very large amount of the energy is delivered in very short period. So, amount of heat actually required for the welding purpose or for fusion purpose is very small. So, here you see these are the two sheets to be welded, and if the the two sheets to be welded must be properly machined, aligned. This is very important in case of laser, accurately machined and aligned. If any gap is left between the two plates to be joined, like say the gap is if say 300 micrometer between the plates due to the machining accuracy or misalignment, if the gap of 300 micrometer is left between the two and we are using the laser of 200 micrometer, then at that location you will see that laser will just pass through the surface of the workpiece, pass through the gap between the plates to be welded without causing any heating. So, it is very important that the edges of the plates must be properly machined, they should be straight and aligned, so that the gap between the plates to be joined is very less or rather smaller than the diameter of the laser which is to be used. So, here if the diameter is larger than the gap which is there, then of course it will result in the continuous melting of the fin surfaces, and this melting will be so faster melting using very less heat input. So, H net is very small in case of the laser melting, laser welding, and if the H net is very small, means the fusion is taking place, like say this one, if this is side view here, then the laser will be generating very you can say not the volume of the weld metal produced is very small, and you can say aspect ratio is very high, means depth to the width ratio is very high, and the thickness for which the laser welding is normally used is 19 mm of the steel. However, using the high capacity lasers, efforts have been made to weld in single pass up to 32 mm also, but it is not so common. mainly up to the 19 mm thickness plates have been welded in single pass. So, here the thing is, since it works very fast, it melts very fast and using the even very less heat input. So, the cooling rate experienced by the weld metal is very high. So, high cooling rate results in certain favorable things and unfavorable things also. Favorable things like high cooling rate results either very fine grain structure, which is good from the mechanical properties point of view, sometimes even amorphous structures also obtained, but sometimes too high cooling rate can lead to the entrapment of the gases in form of porosity, or if the material is hardenable, then excessive hardening can cause the cracking tendency in the hardenable steels. So, this is another problem related to the high cooling rate. Fine, it is good to have the fine grained structure for improved mechanical properties. Sometimes it results in the amorphous structure also, but since the cooling rate is very high, so there is a possibility the gases will get interrupted, or in case of the hardening steels, material may get hardened too much, so leading to the cracking tendency due to the residual tensile stresses. Other attractive features of the process are like reduced heat input, like one factor is this cooling rate. Another is, since the weld volume and HZ both are less due to the reduced heat input. So, this is so the related expansion and contraction coefficient, the volume of the metal which is heated during the welding and then contracts during the cooling is small. So, this in turn reduces the residual stress volume. So, reduction in residual stresses decreases the distortion tendency. So, this is one thing, since this entire volume is extremely heated volume of the weld metal which is produced, and the heat affected zone which is produced in case of laser welding due to the limited heat input for the fusion purpose is less. So, it results in the reduced residual stresses as well as the distortion tendency. Further, most of these joining in case of the laser welding does not use the external filler, just the fusion of the fixed surfaces is achieved. So, mostly it is autogeneous weld. In this case, there is no use of contamination from outside. In which form? Like no electrode, no filler, no electrode, no filler, or no external gases. However, for the good quality purposes, we may use the shielding gases. So, shielding gases may help in improving the quality of the weld joint by avoiding the interaction of the atmospheric gases with the molten metal. So, these are some of the positives of the laser welding. Apart from this, we need to see the capability and the limitations of the laser welding from the welding point of view. So, further, no vacuum requirement in this process, and there are very small and tiny welds can be made. This feature is extremely exploited in joining of the very thin sheets for mass production purpose, because the welding speed is high, thin sheets under controlled conditions can be welded effectively once the process parameters. So, of course, the power and speed, these two need to be optimized properly, so that we get the required depth of the penetration and depth of the fusion. However, the depth of penetration and depth of the fusion are significantly influenced by the process conditions and the material being welded. Therefore, we need to ensure that the consistent penetration is consistently achieved. Now, some of the limitations are also there related with this process. Since the laser beam diameter is very small, so it is important that the workpiece workpieces or sheets or plates to be joined are placed very accurately. Otherwise, we will find that the beam has passed from somewhere else. So, workpieces are placed very accurately to ensure that the beam passes through the center line of the welds, and very limited penetration. It is normally up to 19 mm only. The through thickness penetration weld can be made. It is very common. So, it is like say up to the 2 centimeter only it can be welded, and very good control over the good control over process parameter is needed. Otherwise, we may get inconsistent penetration. And the issue related with this is that high reflectivity materials like aluminum and copper, these impose lot of difficulty related with the reflection, because whatever beam is directed over the surface, it gets reflected, and hardly say 5 to 10% of the energy is absorbed. So, the melting is very difficult, and high thermal conductivity further makes this melting of the copper and aluminum difficult. So, so these materials require a special precaution in order to improve the absorptivity and reduce the reflectivity. It is common for these materials that efficiency is very less, like say 10% only. So, that is why some roughening method, roughening of the surfaces or application of the coatings like the black paints etc., help in increasing the absorption of the laser in case of the aluminum and the copper. Now, we will see it from the penetration or performance point of view. We know that the laser is used in two ways for the welding purpose. One is that heat applied is transported through the conduction, and then melting takes place. This is called conduction mode, and another is keyhole mode. So, what is the difference in these and what happens when the laser is directed on the surface of the workpiece? So, for this purpose, what we need to see is one diagram. Here we have a power density in terms of the watt per square inch in 10 to the power 8. So, here what we have 10 to the power 6, it is here like say 2, 4, 6, 8, 10, 12 like this, and on the other hand the penetration depth which is achieved in inches, it is like 0.04, 0.08 and like this 0.44. So, when the power density is increased, what we get like initially it keeps on increasing linearly like this, and then it jumps fast, it increases rapidly with the increase in the power density. So, this is the zone for the conduction mode, and this is the zone for the keyhole mode. So, here the penetration the width is large and penetration is limited, width penetration increases, width is also high, but thereafter we will see that penetration width is not does not increase much, but the depth of penetration increases. So, this depth of penetration will keep on increasing without increase in the width of the weld. So, this is what is obtained in keyhole approach, but it imposes certain problems like high energy density results in the evaporation of the metal, and metal vapors actually ionize, and ionization of the metal vapors forms the plasma, and this plasma absorbs the laser. So, whenever plasma is formed in this gap, the plasma absorbs the laser, and which in turn reduces the actual energy being delivered to the base metal, and that it in turn reduces the depth of penetration. So, depth of penetration is reduced due to the plasma formation. So, this plasma formation must be taken care of or it must be suppressed. So, either the energy density and the scanning speed parameters are controlled in such a way that the plasma formation is avoided, or if it is being formed in any case, then the flow of the inert gases during the welding is ensured in such a way that the plasma is expelled from the hole which is being formed. So, a proper care is taken in during this process, means directing the inert gases in such a way that the keyhole is not disturbed, otherwise it will get collapsed and it will adversely affect the weld joining process or the welding process. So, this is what you have seen, that depth of the penetration is affected by the energy density and the formation of the plasma also affecting. So, the different metals of course allow the different kind of the depth of the penetration. So, here now I will conclude this presentation. In this presentation I have talked about the basic principles, how the laser beam can be effectively used for the welding purpose, what are the positives or the advantages of laser welding, and in what way it offers certain disadvantages for the laser welding, and what are the points must be kept in mind while using the laser welding for the consistent and uniform penetration during the welding. Thank you for your attention.